We're back with another example for class 24. And this could be the last one of the semester. Last example of the semester. A farmer runs a heat pump using 2 kilowatts of power input. It keeps a chicken hatchery at a constant 30 degrees Celsius, while the room loses 10 kilowatts to the colder outside ambient air at 10 degrees Celsius. Find the coefficient of performance of the heat pump, the rate of entropy generated in the heat pump, and its heat exchangers, and the rate of entropy generated in the heat loss process. All right, so we have a bunch of different things. We want to find the coefficient, the heat pump coefficient performance, rate of entropy generated in the heat pump, and its heat exchangers, and we want to find the rate of entropy generated in the heat loss process. So quite a bit of stuff. Probably something similar to questions you'll be asked at some point. So here you go. Here's the hatchery, chicken coop, and we're going to have a heat pump right here. Boom. It's going to take this outside air because of the work that you put, power that you put into it. So there you go, power in, and this is going to be the QL. And it's going to put, boom, going to go into there, and that's going to be the Q dot H. But we are then going to have some loss, Q dot loss, coming in right here. And I'm going to try to draw a chicken. Looks more like a dove. He's got a little funny little tail. He's not fat enough. And here you go. I don't really know if I've done a good job with him. You can make him into a rooster, so he's more recognizable. I'm not really good at drawing chickens, it turns out. That's interesting. I'll have to take some drawing lessons. And let's see. So it's 30 degrees on the inside, which is 303 degrees Kelvin. That's good news. And this is going to be equal to 2 kilowatts. They told us that. And this losses is going to be 10 kilowatts. And also the outside temperature is going to be 10 degrees Celsius, this ambient air, which is also where we're drawing this thing up there. So just remember that. And all right, so if you do a control volume around the hatchery itself, right here, right? Is the control volume hatchery. Get yourself to a nunnery, get yourself to a hatchery. Chicken. And then we do the conservation of energy. We will find that QH must be equal to Q loss, or Q dot H and Q dot loss, right? So if we have like equals, and then so in is Q dot H, out is Q dot loss. It's obvious. They're equal to each other. So that's equal to 10 kilowatts. So if you want to go to the heat pump, so we could do a conservation of energy heat pump thing going on here. I'll put it right up into the boundary. Conservation of energy. So this is the control volume for the heat pump, HP. We have 0 equal to, I guess, negative Q dot H plus Q dot L, and then it's going to be plus W dot in, right? It's normally minus, but that's because power is usually out. So anyway, what we want to try to find is Q dot L. And Q dot L is, math is hard. I think it's going to be Q dot H minus this. So that's going to be, we just established that it was 10 minus 2 in, so 8 kilowatts is how much, not loss, that's be L, I mean low, the low temperature heat transfer. And then also coefficient of performance. We didn't actually need to find this right here, but let's go to find the coefficient of performance of a heat pump. It's going to be equal to QH divided by the power in, right? What you want over what you paid for. You want to make heat go into the chicken coop. So that's going to be 10 divided by 2, so you get 5. And that's one of the things that we were asked for right here. The rate of entropy generated by the heat pump and its heat exchangers. That's, oh, I guess we're grouping them together. So there is a heat exchanger out here, a heat exchanger right here, I guess like right in there. So we're going between 10 degrees out here and 30 degrees inside there. So, okay, so here we're still using the control volume of the heat pump and find the entropy. And so we're going to go 0 equals Q, coming into the thing is QL over T ambient. And then out of it is going to be Q dot H coming into there. And this is going to be the temperature of the hatchery, and then the generation by the heat pump. So I'll write this out as S gen heat pump. And now, of course, these things flip. So you're going to have the Q. This is going to be, yeah, this is going to be the first one. No, it shouldn't be. One second. I'm not liking that. I think I wrote it wrong. Here, let me pause this. I want to get it right. I was right. What the hell? Okay. The H is 10, right? Yeah. And then the temperature, the ambient temperature is 30. The hatchery, right? That's the hatchery. I want to do this one. 10, hatchery, 303. Should I just write what's on the page? Trust myself? I don't know, maybe. And then this one is going to be 8. And that's going to be 283, right? Sure, because it's 10, yeah, 10 degrees Celsius, yes. And so we end up finding, and then I multiplied it by 1,000, so that I would get, wouldn't get a lot of decimal places. And we get in watts, degree Kelvin, right? Because these are kilowatts right here, degree divided. So instead of doing kilowatts, I did watts, so I multiplied it by 1,000. And then, so that's the entropy generated in the heat pump. And now how about the process here where we're going to go through the chicken coop, right? So we want the rate of entropy generated in the heat loss process. So this is the heat loss process. So we're going to go use the chicken coop or the control volume for the hatchery, right? So that's going to be the control volume for the hatchery. And that's equal to this. Now this is going to be the Q, and this will be the H, right? Because this is equal to the losses, and this is coming into the chicken coop, and that's entering at crossing the boundary at T hatchery minus QH, and still that same heat flow. This is the losses one though, and this is going to be the T ambient. And then we have the generation in the, I don't know what to call it, hatchery. So the S, and this should be dot, hatch, gen hatch, should be equal to this QH. So they're both going to be the 10 kilowatts divided by the ambient, which is going to be 283. And then subtract 10 over, and now this is going to be the hatchery, which is 303. And you're going to end up with 2.332 watts per degree Kelvin. So this is what happens to the hatchery because it's escaping out of the roof in this process where entropy has been generated. You can see more is being generated because of the heat pump than because of the leaky roof. And that's it. I don't know, is this topic worth it? Sure, why not? Talk to you soon.